with nanoglass alloys. And this is what we did here, and I'll show you one example where we see also very spectacular effects. The nanoglass I'm considering here is a nanoglass consisting of ionic nanoglass, a amorphous silicon oxide, and the metallic clusters are a palladium silicon iron glass. So this is a metallic glass, this is an ionic glass, and when we put them together, the surface looks like this. This is not surprising. You see the big blobs, they are the metallic parts, and the smaller ones are the ionic parts. And when we scan across it for the composition, then what comes out is also not surprising. We get very big fluctuations. There's a palladium concentration as a function of position. We have some areas where we have a very high palladium, then zero, high. This is each time we hit a metallic glass particle, we get a high concentration. When we hit a silicon oxide, we get low. The big surprise came when we annealed this material for only about 3 hours at a moderate temperature of 250. What we saw is that all these clusters disappeared, and we got a very uniform structure, and the composition became very uniform. In other words, all these clusters here disappear, and they form an amorphous solid solution of an ionic material in a metal. This is something you could never do in the crystalline case. If you have, say, silicon dioxide and iron, you can do whatever you want. It will never form a solid solution. Now, in this case, it does form solid solutions, and we tried some other systems, always the same answer. We can mix and alloy components which are immiscible in the crystalline state. So this is a very fundamental progress. When you look in earlier days, Bronze Age, Iron Age, Semiconductor Age, it's always that you take one component, tin and copper, and you get bronze. Or iron and nickel, you get a steel. But now we can alloy components like silicon dioxide or silicon oxide in a metal. So you can alloy a window glass with a piece of iron in this state. If you look back now, of course, that's not quite surprising. You think about it. When you have sugar and ice, you cannot mix it. When you have honey and water, you can mix it. So this is exactly what we see here. In the amorphous state, we can mix components that are immiscible in the crystalline state. And that opens up a whole new world of alloys where we can then mix ionic with metallic materials. In other words, if we change the chemical composition, we can tune the bonding of the material from an ionic material all the way over to a metal. And depending on what composition you choose, it's more metal or more ionic. And the metal is no longer a normal metal, because then you have sitting the ions of the ionic materials in the metal. That means the conduction electrons have to screen these ions. They are either repelled or attracted, so we get very large fluctuations in the electron density. This is a very new material. It should have new properties, electronic, optical properties, and so on. All we have so far, what we know is that we can do it, we know how to do it, and that we form a family of alloys which did not exist in history so far. Now, so far, all the things I've considered here are, of course, electrically neutral materials. We have these clusters, and they are electrically neutral, bring them together, and we are now. What I want to do is go one step further and go to nanoglasses, which are electrically not neutral anymore. In order to do that, we did the following. We take a two-phase nanomaterial, here black and white, this black and white, and then we etch out the one component, say the black one here. An example of that sort is a gold nanoglass, and we etched out the other part, and then you get nanometer size holes inside of the gold. And the structure looks like this. This is the gold, and this is the material which is etched out. And now we fill in an aqueous electrolyte into these voids, and then we can apply a voltage between the electrolyte and the metal, the gold, for example. And if you do that, then of course we get electric charges at these interfaces, and as 50% of the atoms are sitting in these interfaces due to the nanometer scale structure, then of course 50% of the atoms can be changed in their electronic charge. So we can tune the charge of the atoms in the way we can do it and by applying the voltage. And that, of course, changes the properties. We tried that for a few systems. I'll show you 3 examples. The one is the charge-induced superconductivity of strontium titanate. Strontium titanate in the pure form is an insulator. And what we did, we have a strontium titanate, thin film, electrolyte, KClO4, and here a platinum gate, and we apply a voltage. And what we can see is when we apply a voltage and charge the strontium titanate highly, then the surface of the strontium titanate becomes a superconductor. And you can see here when we apply a voltage of about 0.4, we get a superconductivity at 0.4 Kelvin, so we can transform it from a normal conductor in a superconductor and back. And the same we can do with porous strontium titanate, where most of these atoms are sitting in the interfaces, so the entire strontium titanate can be switched between a superconductor and a normal conductor. Another application is artificial muscles. By using the charge density-induced variation in length of carbon nanotubes, we can build artificial muscles. What we do is we have the muscles and they are sitting in an electrolyte, and when we apply a charge, then these carbon nanotube threads twist, and when we decharge them, they untwist. So you can see here the twisted state and the untwisted state. And by twisting and untwisting, the length of the carbon nanotube changes. And so when you put that into the body, at a position where somebody has lost its muscle, you can, by applying a voltage, shorten and lengthen this structure, and that acts then like a muscle. If it is short, then the arm will be stretched. If it is long, the arm will be bent. There's, of course, a spring on the other side. So these materials can be, or the charge-induced length variation can be used for building artificial muscles. The third example I wanted to show of property changes, which is also very dramatic, is the magnetic moment of palladium-nickel nanoclass. By applying an external voltage of about -0.4 to +0.4, you can change the magnetic moment of the nickel by about 45%. So you can again switch the material forth and back by having this locally very highly charged state. So that is a new aspect of the nanoglass, that we can now change properties by applying external parameters like a voltage and change then the properties. A last factor also which opened up with the nanoglass are materials where we can have switchable atomic structures.